Maybe if
Oh,
we
it's my
press,
Zoom. So here, I started recording.
great, great. So, sorry, first things first, how should I address you?
However you want, Stephen, whatever. I don't know. People usually, the honorifics don't suit me terribly well.
Okay, great. So is it okay if I call you Stephen?
Absolutely.
Great, great. So, and I'm Trishank. Been a long fan of yours, at least 20 years, if not more. So this is a dream come true. Thanks for taking the time. Really appreciate it. I remember buying your book as a young man when I was out in Malaysia, and I used one of my first paychecks ever. It was a significant portion of my paycheck just to get the hard book. It was lovely.
Well, I was a younger man when I wrote that book 20 years ago. In fact, the book came out May 14th, 2002, and next week will be the 20th anniversary of a wrap party that we did for the people who'd worked on producing the book. And yesterday we pulled out the pictures of that party and met up with those people. I have to say, I think we aged fairly well, mostly. I think I was at the end of spending a decade working on that book, kind of the most difficult single project I've ever done. I think I was in my all-time worst personal kind of, overweight, badly, et cetera, et cetera, et cetera. So it's been good since then, so to speak.
That's great. I saw your blog post about how your working model too. You have this excellent treadmill, and you get a lot of exercise done, even if you're at the airport. That's amazing.
Yeah, right.
So
let's see. So what should we talk about?
Yeah, good question. So my rough agenda is basically a walkthrough of your physics project. And I'd love to talk to, so I'm going to begin, if you don't mind, by me trying to summarize the main ideas. Hopefully I don't butcher it too much, and then you can tell me where, if I got it right or which pieces I got it wrong. I especially want to talk about the Ruliad space, which I find incredibly fascinating. And then we go back in time and talk about your book, ANCOS, a new kind of science, and specifically a principle of computational equivalence, and how I think it relates to some of my ideas on why IQ is largely not a very good measure of human intelligence, I think. But we'll go there. And finally, some questions about things like AGI and everything. Does that sound good?
Sounds interesting. Let's give it a try.
Great. Yeah. Okay. So let's see. So let me share my screen. Okay. So and this is lovely. This is kind of like pandemics have, of course, have terrible downsides, but the upside can be that people like yourself, last time there's a pandemic in England, Newton came up with Principia Mathematica, and now yourself and friends have come up with this wonderful physics project, which is great. So my rough understanding is, so I really like it as a computer scientist because you start with one of our favorite data structures, which is a graph. But you use a hypergraph, which is a lovely generalization of it. So basically there are rules. You think that space is made out of this thing called atoms of space, which you can think of as nodes or vertices in this thing. Mm-hmm. I sometimes call them spacions.
That's interesting. That's a word I haven't heard. Okay, coin that word. Yeah.
So you've got the spacions or atoms of space, and you have rules, deterministic rules, if I understand them correctly. Where you say, for example, if you've got nodes x, let me see if I got this right. So you've got connection between these nodes, right? And sometimes you want to rewrite the connections between them. So you might add new connections or remove them, and even add new nodes in the space or even remove them, which is interesting. Yes. So I've been thinking. Sorry, go ahead.
No, that's right. That's right.
Great. So
it'll get, I don't know how computer sciencey you want to get, but one of the things that, you can think about new nodes as being like, bound variables inside lambdas and so on. And so in a sense, as you create atoms of space, it's like our whole universe is escaped bound variables, so to speak, which is kind of a ironic twist. It's like, that's often will be viewed as a bug in a functional, writing functional programming code if you have escaped variables from a lambda. Yet in this theory, in a sense, the whole universe is made of escaped variables.
Interesting. So sorry, lambda calculus, I've never got too deep into it. So if you could give a brief refresher of what bound variables and escaped variables mean.
It's probably not worth it. Sorry, I was just I was kind of riffing on the computer science angle of this. It's
Gotcha.
It's not a useful analogy unless it's something you kind of live and breathe type thing.
Gotcha. I should take a deeper look into that. I'm gonna explore it. But basically a hypergraph is a generalization of a graph where if you have an edge, it's not just between a pair of nodes, it can be between any number of them, 3 or 4 or 5 and so on.
Right. The particular kind of hypergraph that we're using is one where you can have relations between nodes and those nodes appear in a particular order in that relation. So it's like in a graph, you can have a directed graph where there's an arrow which goes from one node to another, or you can have an undirected graph where you can kind of go in either direction. This is kind of a version of a directed hypergraph. But again, these are technical details. This is what happens in I'm so used to explaining this to people. I'm not so used to people explaining it to me. So but it's good. It's keep going. Okay, we're talking about hypergraphs in space.
So in a way, it relates to your latest. I saw your latest talk about science and technology for kids and others, where you talked about. So you've got this idea of how concepts or words travel between people. So I guess this is a live example of that happening.
Yes, right.
Okay, so you've got these rules and you've got this, right. So you've got this hypergraph where there's a directed relationship between nodes, and you've got a sequence of events when you apply these rules. And actually there's an interesting detail where you can have more than one sequence of updates because there's different ways you could update this thing at once, right?
Yep.
And when you keep applying these things over and over, you basically see, well, I suppose if you have the right set of rules, you see space expand. I guess it's possible to have a bad set of rules where space accidentally shrinks and
absolutely, and the universe ends.
Right. That would be a closed universe, right? Yeah.
Well, what ends up happening, I think, actually, time can end if there are no more rules that can be applied. The progress of time is the progressive application of rules. If there are no more rules to apply, time ends. And that's actually what happens in the center of black holes.
Correct.
At space-time singularities or space-like singularities, the one has a situation where basically time just stops. And what you see here is that means there are no rules that apply. So if sort of an interesting point, you made sort of passing reference to this thing called the Ruliad, which is this sort of universe of all possible rules. In a sense, one could say in some directions in the Ruliad, time stops. But the very existence of an observer must live in a part of the Ruliad where time didn't stop, because otherwise you don't get to be an observer who has a notion of the passage of time if time already stopped for you.
Right.
So actually, I had not thought that through with good clarity. So I haven't thought that through after understanding these things about Rulial space. But I think that's the correct understanding of it.
That's great. So unless I suppose you're one of that unfortunate astronaut who falls into a black hole, but then they say that you never stop falling into a black hole. So I'm not a physicist.
Well, no, the thing that happens is time stops. So you don't, it's like your computer is frozen. You're frozen. You don't sense any passage of time.
I see.
And the universe around you doesn't progress in time, but nor do you.
Everything just stopped. Okay, interesting. Gotcha. Okay.
So it's I suppose in the future world of digital consciousnesses and things like that,
right.
It'll be like you froze for a century, and time, it's time stopped for you. But if there's, it's a question of, did time stop for the whole universe around you, or did time just stop for you?
Right, right. Which is the whole point of. Sorry, go ahead.
If you're living in some game, and the game freezes, then both your avatar and everything around it freezes, so to speak. And it's that's the same situation kind of as falling into the black hole.
Gotcha. And that's basically relativity, the perception, the perception of time and how events flow depending on where you are in this space.
Well, that's a very extreme case. I mean, time stopping is a very extreme case. That's what I mean. Photons, for example, things that travel at the speed of light. Time does not pass for something traveling at the speed of light. So a photon emitted at the 100,000 years after the beginning of the universe, when the universe became transparent, can have been moving towards us all that time as we perceive it. But as far as the photon is concerned, when we absorb that photon in a detector for the cosmic microwave background, that photon, as far as that photon is concerned, was just created, at the Big Bang, and no time has passed. And in our model, that actually has a very clear way of being understood, which is that when you have a certain sort of, there's this computational process you mentioned, kind of the rewriting of this hypergraph, and there's sort of a certain amount of computational effort that's spent rewriting the hypergraph. If you move, then in order to sort of execute motion, you have to recreate yourself at a different place.
Right.
And that takes computational effort. And you've got a choice. Do you want to use your computational effort evolving where you are, or moving to a different place? And as soon as you use computational effort moving to a different place, it means you don't have as much computational effort to spend evolving in time. And that means that's why time dilation occurs. That's why time appears to slow down for things that are moving. And the extreme version of that is a photon, which is traveling at the maximum speed with respect to physical space. And that's so time basically stops for a photon, so to speak. So it's rather nice that it's possible to have this kind of computational intuitive understanding of time dilation in our models, because that's something, time dilation had always seemed like a thing where it was sort of a logical necessity given certain assumptions about space and time, but it's not something where one could sort of understand mechanistically why it happened.
That's a really interesting new way to look at it. I've never heard motion described that way. And that explains why time stops for you. Interesting, because you're expending energy on something else, which is motion, pure motion, I think you call it.
Yeah, right. Well, I mean, you expend computation. I mean, the thing is, the very fact that motion is possible is not trivial. Like, everything's made out of atoms of space.
Right.
But every time I move, it's different atoms of space that make me after I've moved. And so the fact that it's still the same me after I moved is not trivial. It could be the case that to move from here to there, it's kind of like Star Trek transporter all the way down, so to speak, that you have to sort of, you have to rewrite yourself in some completely different form, be transported to somewhere else, and then recreate yourself. But the fact is, we have this idea that in space, it's a very non-trivial fact about space, that pure motion is possible, and that it's possible that you can take a thing which is sort of the integrated you and just move the whole thing to somewhere else in space without sort of destroying it and recreating it. And I think the thing that it doesn't always happen. If you're near a space-time singularity, even in traditional theories of gravity, you'd be shredded to pieces by the kind of by the fact that there's all this curvature in space right at that point.
It's basically rewriting you. You disappear. That persistence goes away.
Yes. I mean, the fact that it is consistent for us to believe that we persist in time is a pretty non-trivial fact about the universe, or at least about our way of perceiving the universe. That is the fact that imagine, you can kind of think, imagine you're a computer, so to speak. And there's a question of, can you imagine, and I haven't thought this through very well. I actually was thinking about this because I was trying to, I've talked a bit about consciousness and the way that the way that consciousness kind of plays against physics and against our perceptions of things. And so I kind of, as an exercise, I was trying to write out, if I was a computer, how would I view the world? And it's kind of like between the time when you start your computer and when you shut down your computer, that's kind of one computer life. And you build up a certain amount of memory about what happened, and you might leave, your descendants, you might leave some data on the disk for your descendants, so to speak. I think the question of so it's kind of from inside the computer, what is its perception of what's going on? And these kinds of questions about whether it has the idea that there's sort of a persistence to its existence, even though, for example, that process, the operating system that's running, it's moving around, it's running, it's got different pieces of computer memory are being used and so on. But yet, in some sense, there is a consistent thread of existence, so to speak, for the computer, I think. And that's it's sort of interesting to try and project oneself. It's not, project yourself into a computer, so to speak, and imagine what it would be like. But we're getting off track. Please go on with.
No. That's a very. I was gonna say something else. Right. Persistent. It goes back to that old philosophical problem. I forget what the fellow's name was. But basically, if does the same man step into the same river twice?
Heraclitus.
There we go. Exactly. And my answer is like yourself. I suspect is yes, because it's not about the exact nodes, spacions, or atoms of space, whatever you want to call them. It happens to us, even life, living matter. Our cells are being dying and growing all the time, yet we have the perception of being the same. And I think that's because, and this is an idea you get from computation, because what matters is the network, is the structure.
Yeah, right. Well, it's kind of like, one of the things I found interesting is that, obviously our physics project is built very much on this kind of giant tower of modern science. But a lot of the questions that are sort of foundational questions are ones that really haven't been thought about that seriously for 1,000 years or more. And, back when they were being thought seriously about, theology was the leading kind of intellectual field. And so a lot of these kinds of things are things that there are sort of theological discussions of. Like, for example, the thing you just mentioned, what is a soul if it isn't something that is sort of the computational engram of the thing that is us, for example. And, I know, back when I was a kid and things, people would sort of, mock the notion of a soul with the kind of, how much does a soul weigh? It's like a soul, if it exists, it must be a physical thing. You can put it on a weighing scale and so on. But now that we understand computation better, we understand there is a thing that can be in some very meaningful sense real, but not be something you can put on a weighing scale as such and sort of say, oh, it's a physical thing like that. So it's sort of interesting that in the history of ideas, that this notion of a soul, for example, that came before modern science, is something that in fact is very much an idea that they just didn't have the way of expressing things in terms of computation and the abstraction and so on. I mean, for me, it's kind of a cautionary tale, because it's like, what are things that we think about today that seem like they're kind of, that we can't really describe very well, which when there is a new framework for thinking about them, it'll be like, well, that's obvious. That's, it's clear. And one of my favorites along those lines is back in the day, it was kind of a big thing to think about making a computer. And then now we have a few, tens of billions of computers or something in the world. But my assumption is that in the future, one will think of everything as being made of computers. Just like, 100 years ago, plastics got invented, things started to be made of artificial materials. There will come a time when it is routinely the case that everything down to the molecular level is in some sense, programmable thing. Now, I think that it is the case that in everything, this principle of computational equivalence of mine, everything can be thought of as doing a computation. But this idea that maybe there are sort of engineerable computations that are engineerable down to the molecular scale is one that I suspect is one of these things. If I project of the things that we do today, that where we say, oh, this is how it has to be and so on, what will look incredibly sort of Stone Age or something in the future. and I suspect that's one of them. Another one is the idea that when you look at something like a gas with a bunch of molecules bouncing around, the idea that all we can talk about is, pressure and temperature of the gas, that will seem incredibly Stone Age. And people will say, but look, there were a trillion molecules there doing all these complicated things. How come you ignored all of that? And all you could say is what the overall pressure of the molecules was. I think that's, but it's always interesting to me to try and understand sort of what are things where you can foresee where, the things we're thinking about today are sort of inadequate. But anyway, I'm derailing us again.
No. I love derailing. This is a bit like a fractal. We're exploring different parts of the picture. So this is great. Digressions are very good. Speaking of souls, I love this is very good, because I think I used to be one of those atheists who, I went through that phase myself. But when I was young, I was religious. And then I went to college, and then becoming an atheist was cool, I guess. And I used to make fun of the soul too. But now, recently, after having read people like yourself, and have you read Douglas Hofstadter's "I Am a Strange Loop"?
I haven't read that one. No.
You might like it, because I think he goes through the idea of having a computational notion of the soul. So I really like this, that we can take ancient ideas that really do have a lot of merit to them. They're not complete, made up concepts. People have been thinking about this for thousands of years. So it's great that we can now finally give a computational framework to it. So that's lovely. Oh, and the other one that it reminded me of is Frank Tipler. Unfortunately, his model apparently doesn't work. He's a Christian who's also a physicist. I'm sorry, I'm not sure if you're aware of the, might be explaining something you already know.
No, I've heard of Frank Tipler's stuff. I don't know it in detail.
Gotcha. So he wrote a book called The Omega Point. Yeah, I believe it's called The Omega Point. I haven't fully read it myself. It particularly requires a deep knowledge of physics too. But anyway, the idea there is that he has this idea that in the future, you can build this computer so powerful, it's basically an AGI, I think, that you're basically building God from machine and resurrecting humans in the form of computation, and recreate heaven. So it's a really interesting theological and computational.
Well, I think that one of the things that I've found interesting in our project and so on, I mean, this things like, why does the universe exist, which even the theologians have avoided that question. That question has been thought to be really hard. The surprise in our physics project is that we actually have an explanation. We have and the explanation ends up being, there we go, that this is all about this thing that I call the Ruliad, which is kind of the entangled limit of all possible computations. Okay. So you say, and that's something which in some sense necessarily exists. If you say, well, I've got a particular computation, I'm going to pick, this is the one, I'm God, and I'm going to pick the computation for the universe, then you need a God with sort of agency to do that. But if you say, I'm going to look at this thing that's all possible computations, right. Their structure has a sort of necessary character to it. And then the question is, as entities embedded within that structure, how do we perceive that structure? And the surprise to me is that only, recognizing only a couple of characteristics of us, like we're computationally bounded, we believe we are persistent in time. Those characteristics alone cause us to perceive this necessarily existing Ruliad in ways that correspond to the ways that we know the laws of physics work. And so, in a sense, the universe necessarily exists, and it necessarily exists in the form that it appears to exist for us because we perceive the universe using the means of perception that we have. So in other words, there is a universe of all possible universes, and if we were aliens built differently, we would perceive a different universe. But the universe as it is to us exists the way it does to us because we have the forms of perception that we have. And it's kind of like there is one sort of a contingent fact about the world, which is that we exist at some place in Rulial space that corresponds to some particular set of ways of interpreting the universe. And that's, I mean, I find that I mean, it's surprising that one can say things like that. So there is another fact, which is there is another contingent fact, which is in addition to the Ruliad, which is the entangled limit of all possible computations of the kind that you can do with like a Turing machine, there are an infinite hierarchy of hyper-Ruliads, which are things that basically are doing computations that are done by oracles of Turing machines, by machines that can answer questions that would take an infinite time for a Turing machine.
Hypercomputers, yeah.
Yeah. But the point is that it is just essentially an abstract, formal, mathematical fact that there is an event horizon between the Ruliad and the hyper-Ruliad. So even if the hyper-Ruliad in some sense exists, and presumably it does, we are forever locked within the Ruliad and never able to sense the hyper-Ruliad. So in a sense, the contingent fact about the world is that we exist in the Ruliad and not in the hyper-Ruliad. So in other words, it could be the case that, you know, just like we exist at this particular place on this planet, you know, on the outer part of this galaxy, et cetera, et cetera, et cetera, that's a contingent fact about us in the world. So also it is a contingent fact about us in the world that we exist where we exist in the Ruliad and not in the hyper-Ruliad. So that's, I mean, so in a sense, that's the, but to me, the fact that one can even have a meaningful kind of science level discussion of these things is fairly remarkable. And you know, it is a project I'm just starting to do to kind of go back and really catalog what philosophers and theologians and other people have said about space and time and consciousness and perception and so on. And I think that you know, for me, I've always had a hard time understanding what they've said. But now that I have sort of a hard basis where I can just run a program, you know, write a piece of Wolfram language code, run the program, and you know, see what it does. You know, I feel much more empowered to go and look at those sort of philosophical questions and see if I can kind of untangle them in our context. I mean, you know, there are questions from that I sort of looked at much longer ago, like free will versus determinism.
Right. And
you know, to what extent does, you know, in a sense, one clearly doesn't have free will if something from outside one can just say, and they're going to do this in the end. Then it's, you know, that's kind of a manifest version of a lack of free will is somebody knows what you're going to do.
Right.
And so the thing that was a big surprise to me is this idea of computational irreducibility that I came up with in the 1980s, that says that when you have a program, even a very simple program, we should bring up a picture of Rule 30. If you can, I can
sure.
find
Yes,
one.
yes, absolutely. Or I can bring it up in chapter 2. Yeah. Look at that. First, a legal document shows up, which is hilarious. So that's it is. Oh no.
Just try. You can go. No,
is this good?
Go to chapter 2.
Chapter 2, great, yeah.
And go to that there in the middle. That one there. Yeah, that's a good one. Okay, so this is Rule 30, and that's interesting. I haven't ever tried typing Rule 30 into a web search engine. I don't know. I'm going to
complain to Google. The wrong thing.
But the idea here is that it's, you know, a line of cells. Each one is either black or white. It's going down the page, and at each step, one's just updating the color of a cell based on that little rule down on the bottom left there. And if you go, I think, to the next page, press the arrow that goes to the next page. Next page. One more page. There we go.
Lovely.
That's what happens after a whole bunch of steps. And the big surprise is that it's a big surprise, so to speak. That is that from that rule, you can't readily foresee what's going to happen. And the question is, in general, when you're shown a rule, can you predict what will happen? And we've tended to get used to the idea, well, when we build things in engineering, we tend to make things that we specifically construct so that we can foresee what they will do. And so we don't want something like this in the traditional approach to engineering, because we couldn't foresee whether it'll do what we want.
Bad for business if you couldn't control it.
Right, yes. I mean, it may be, but it's what has happened in nature forever, but it is not something that, in the past, we've kind of avoided computational irreducibility. So computational irreducibility is the statement that if you want to know what this thing is going to do, pretty much the only way you can find it out is to just follow the steps in the rule and see what it does. And you can't kind of jump ahead and say, and the answer is going to be 42, for example. And so the question is that my belief about sort of how the concept of something like free will works is that we are executing computationally irreducible computations. And so that means that the passage of time is basically the progression of an irreducible computation. And so that means that is time. And in fact, in our model of physics, that really does end up being what time is the progression of this computation. And so in a sense, it is both, you might say, big problem, we can't predict what's going to happen. Mm-hmm. And yes, there are, for certain kinds of things in the world, you'd like to say, well, we'd really like to be able to predict what's going to happen with, some grand meteorological phenomenon in the world or something. But we're stuck with computational irreducibility. We can't predict what's going to happen. You have to just follow the steps and see what happens. That's kind of the bad news. The good news is, if you're an entity that's sort of following those steps, somebody could say, hey, wait a minute, you don't need to lead your life. The answer is going to be 42 in the end. But the fact is, computational irreducibility is kind of telling you there is something meaningful that is achieved by the passage of time. There is some irreducible thing that's achieved by the passage of time. And that's and I think that's kind of the notion of the perception of free will is a perception that you can't tell what's going to happen. It is just happening for you, rather than from the outside, something being able to say, and this is what the answer is going to be. So it's another example of where sort of computational ideas kind of intersect with fairly long-term philosophical thinking. But I think we may have derailed from
no, which is fun. Like I said, derailing is good. Like I said, it's like a fractal exploration of the idea. It's wonderful. So sorry if I could just add a few notes to your thoughts there. Yeah. So your exploration of this what look like simple machines, but they're anything but simple. I mean, the word is they're generally very complex, endlessly complex. You see undecidability propping up. You see universality propping up. Sorry, I'm kind of banding around these terms. Maybe we'll explain them later.
I can explain. Yeah. Let's explain them. I mean,
Sure.
The question is, when you see something like this, what is it that you're looking at? Well, one thing that you would say in modern time, if somebody had made a mosaic of this in 2000 BC, they would have just said, well, we just made this mosaic. Today, we have sort of a conceptual framework to talk about things like this. We say it's a computation that's going on. We're seeing the steps in a computation. And sort of there's a question about, if you look at different kinds of computations, how do they correspond to each other? So back, if you'd gone back, I don't know, 150 years ago, most people, you'd said, I want to make an adding machine. I want to make a machine that computes some other thing, I don't know, GCDs, something, right. I don't know what it is, whatever, some multiplication, whatever. People would have assumed, oh, I'm going to go to the adding machine store, I'm going to buy an adding machine, there's a different physical object that will be the multiplying machine. But then the big thing that was first sort of hints of it, well, actually in the 1800s, but then serious hints in 1920, then Turing machines in 1936, Gödel's theorem in 1931, the thing that arose was this idea that, well, actually, that isn't the way it is. You can have a universal machine which has the exact same hardware, the exact same rules, the exact same mechanism, but by feeding it in different initial conditions, by feeding it in different initial data, you can get it to do any computation you want. you can make it emulate any other machine by just giving it the right initial data. And that was, what's that?
And itself, not just any other machine, but itself, which is the
oh yes, it could also emulate itself, although more slowly. That is, you can. I think the emulation of itself is amusing but confusing. I think. I mean, I think that the important part as far as okay, so the question then, so that is a universal machine, a machine that is capable of emulating any other computational system. When people first invented those things, even Turing, Gödel, things like that, they didn't know that those would actually cover everything in the universe. They thought this was just a model of computation. Gödel was pretty sure human minds could go further than the general recursive functions that he talked about. Alan Turing didn't know either, but when Alan Turing studied biology, he kind of went back to things that were beyond Turing machines, so to speak. So it's really a new news, in a sense, that this idea of computation that arose with Turing machines and so on, that the universe really is computation all the way down. I mean, that's something that, you know, when I started thinking about computation, its relationship to science in the 1980s, that was something which nobody believed. It was like, physics is different. Physics is not about Turing machines. Physics is something that involves real numbers and differential equations and all this kind of thing, which aren't about Turing machines. They're a different level. They're sort of a hybrid computational level. And I think our physics project is really pretty extremely good evidence that it really is computation all the way down, and that these things that were discovered 100 years ago as this universal notion of computation, it really is truly universal to the universe, so to speak. So that's kind of that idea. And then you mentioned undecidability. I mentioned computational irreducibility. So so the first point is universality is something that for a long time, it seemed like it's a difficult thing to achieve. You have to go to a lot of effort to achieve it. You know, when Alan Turing first wrote down a universal Turing machine, big complicated construction, et cetera, et cetera, et cetera. If you go to the website, I think it's actually called turingprize.org.
Yes, no one's, turingprize.org. Okay, I see.
Okay, this is, so that's the very simplest Turing machine that exists, that's possible to exist. So, you know, Alan Turing thought universal computation needed a big, complicated machine. We might think that, you know, we have our computers that have 1 billion transistors in their CPUs. We might think it's really difficult to get universal computation. But in fact, one of the things that came out of my efforts to study kind of the computational universe of possible programs is that actually there are programs, it's very easy to find a program that is that is capable of universal computation. And actually the general idea is this thing I call the principle of computational equivalence. That if you have different systems, then as soon as a system doesn't do something that's obviously fairly simple, it's probably going to be capable of computation as sophisticated as anything. So in particular, universal computation.
Right.
And so, for example, this particular Turing machine is a piece of evidence for the principle of computational equivalence, that this is the simplest Turing machine that doesn't do obviously simple things. And by golly, it turns out to be universal. And so
you suspect Rule 30 is universal too.
Yes, although I hope it'll be proved in my lifetime. We'll see. Might take another few hundred years.
There's the new prizes for Rule 30, no?
Yes, that's right. I have
still open.
This is I didn't even put the universality there. I think it's too hard. These are much more. So for example, the center column that seems random, it's like prove that it doesn't just become periodic. It's like prove that digits of pi are random. The digits of pi are fairly easy to produce by a construction, but yet we know almost nothing about them. The digits of pi, the big achievement was it's proved that they don't repeat. They never become periodic. It's not proved that 0 through 9 occur with equal frequency or anything like that. It's not proved that all kinds of wild things don't exist in the digits of pi. Rule 30, same story. It's we know little about it. But the concept here is, so this idea of principle of computational equivalence, it's all these different systems are equivalent in their computational abilities. So if we want to ask the question, we've got one of these systems, we've got us with our brains and our computers and our mathematics and so on. It's like, can we outrun those systems? And the answer is, well, if there's this principle of computational equivalence, we are just computationally equivalent to all of those systems. So that's why we don't get to outrun them, and that's why the principle of why computational irreducibility is a thing, because we are no better than those systems. We can't computationally reduce what's happening in those systems. So then the idea of undecidability that Gödel kind of developed in 1931, that idea, and Gödel's theorem is a little bit, it's a bit more, it's a slightly differently stated kind of thing in terms of mathematical axiom systems and so on. But the thing that undecidability is, let's ask the question in Rule 30, what will happen in the end? You know, if you go 1 trillion steps, what's it going to do? Right. If you go an infinite number of steps, what's it going to do? Well, if there's computational irreducibility, then to find out what it's going to do after an infinite number of steps takes an infinite amount of computation. Right. And so you have to say that that's something not accessible, undecidable to a computational system as can be built in our universe.
Maybe in the
I might mention about Gödel. Yeah. You know, Gödel had a view of mathematics when Gödel proved Gödel's theorem. What was Gödel's theorem? So Gödel's theorem was basically asking the question, with axiomatic mathematics, if you say mathematics is based on axioms, you know, Euclid had developed this idea, you know, just start with 10 axioms for geometry, you know, things like a point is something which has no part, you know, a line goes between 2 points. Euclid had the postulate, you know, fifth postulate, no parallel lines never cross. Given 10 such axioms, Euclid derived 460 theorems of geometry. And, you know, people have this idea that you can start from this axiomatic foundation and then build up everything, so to speak. And that became sort of the core idea of mathematics. And people like Hilbert around 1900 were saying, mathematics is just, you write down axioms. It doesn't matter what the axioms are. You can just write those down, and then you can build all of mathematics. And people were saying, you know, we can just build a machine that will spew out the true theorems of mathematics. And so Gödel wanted to prove that wasn't true. And so what Gödel did was he said, well, you know, he took Peano arithmetic, which is an axiom system for arithmetic. And he asked the question, let's imagine that we could have a statement like, this statement is unprovable. Then that clearly can't be proved. But because now,
but you said in trouble.
What's that?
Because if you did, you'd be in trouble.
Absolutely, right. But people would say, well, that statement is all well and good, but it's not a statement about arithmetic. That just has nothing to do with arithmetic. So what Gödel did was he showed that that statement can be compiled into arithmetic. That statement can be stated as a statement about equations involving integers and things like that. So he basically built the first compiler, in his case, from statements like that, almost philosophical statement, down to arithmetic. And that was kind of, you know, Turing really cleaned up that idea by talking about Turing machines as a way to, but what Gödel had this strange statement. You know, Gödel believed that what he had done there was to basically blow up axiomatic mathematics. But Gödel himself believed that the human mind, has direct access to the truths of mathematics. And what he thought he was doing was to explode this sort of outer shell of axiomatization that people like Hilbert had introduced. Now, I have to say, I didn't understand what Gödel thought he had done until maybe a couple of months ago. Because I've been thinking about the foundations of mathematics and this question of to what extent is, you know, what really is mathematics? And is mathematics kind of just an axiom system? I think I talked about, I haven't really written, I've got a giant tome that I'm just writing now.
Gotcha.
Yeah, there's some little pieces in this. This was a precursor footnote to the tome that I'm in fact hoping to finish in the next few days. it's the tome that I'm writing is called The Physicalization of Metamathematics.
Are you planning to publish it, or will it be online, or both?
It'll be online. It'll be
yeah.
out and about as everything. It'll turn into a book as well, but it'll be it's basically it was one of those, I'm just going to write a short thing, and pretty soon it's 200 pages long with 1,000 pictures and so on.
Right.
It's the thing that so, well, I can kind of, maybe I cut to the chase, because it's kind of it's not obvious that we should be able to do higher level mathematics. That is, that we should be able to talk about things like, oh, I don't know, the Pythagorean theorem or triangles or whatever. It could be the case that the only solid way to do mathematics is in terms of axioms, sort of low level axioms. And that the Pythagorean theorem, there are many different ways it could be stated in terms of axioms. And that every different way of stating it would lead to different kinds of conclusions about geometry, for example. But it is an observational fact that we can meaningfully talk about the Pythagorean theorem. You know, I remember when Fermat's last theorem was proved, I remember asking the person, Andrew Wiles, who'd done that, I said, what axiom system do you think you used? He said, basically, I don't know and I don't care. As in, you know, the truths of mathematics as we humans deal with them are at a higher level than this sort of bedrock, this sort of machine code of axiomatic mathematics.
Too low level for humans to operate, I think, is what you're trying to say.
Right. But the fact is, that's what people have believed the foundations of mathematics are. Gödel didn't believe that, but that's what Hilbert and most modern mathematicians would believe, that in the end, everything can be stated in terms of the axioms of set theory or whatever else. And that's something where the thing, well, this Ruliad idea of mine is something where what we realize is that mathematics, like physics, is rooted in the Ruliad. That is, just as physics is one way of us perceiving and sampling the Ruliad, mathematics is another way of doing that. And so that sort of perception tells one that just as there are physical observers with certain characteristics that are associated with the way that we humans work, so also there are mathematical observers that have certain characteristics based on the way that we work when we're playing mathematicians, so to speak. And so I think one of the big results that is the following thing, that the possibility of higher level mathematics exists for the same reason that we believe in space. That is, it could be the case that we're reduced to just saying, there are all these atoms of space and they're all doing these complicated things and they're in this complicated network. And we never have a higher level view of space. But the fact that we can kind of have a higher level view of space happens for exactly the same reason as the fact that we can have a higher level view of mathematics. And that means that in a sense, the mathematics that we perceive is, in a sense, we're perceiving it with the same kind of mechanisms that we're using to perceive the physical world. And so this kind of gives one the idea that the axiomatic level is just kind of a layer. It's a particular way of sort of parameterizing what's going on. And there is a way in which we humans are going directly from sort of our minds to the sort of raw material that makes up mathematics. So this is, it's very much the kind of idea that Plato had about what mathematics is. It's the idea that Gödel kind of sort of got from that. And turns out there's a lot of truth to it, which I had not realized until very recently. I mean, I'd always assumed that really mathematics was sort of an axiomatically based thing. I mean, it's interesting to compare that. By the way, this whole axiomatization thing, you know, when it comes to the world at large, there's sort of the question of, okay, let's define the sort of human world. Let's put up, you know, laws, a constitution, you know, we want to define how the world should work. Yeah. That's like an axiomatization of things in the world. And there's the question of kind of what, you know, for example, is there an axiomatic system that will guarantee that only the right things happen in the world? Answer, no, for the same reason that there's undecidability.
Yeah,
for the same reason. I mean, it's kind of, I'm a little bit charmed that there seems to be in some parts of the blockchain world, there seems to be an idea that if only we could base the governance of blockchains on set theory, everything will be solved.
Wait, really? I haven't heard of this one. This is hilarious. Yeah.
I mean, it's an interesting, you know, it's a very interesting thing to raise. It is, in a sense, an interesting mistake, because you might think that sort of this mathematical foundation is a bedrock, but it isn't. The thing that's become clear from the studies, the sort of physicalization of mathematics, is that the axiomatic level of set theory is not the bedrock of mathematics. There's things far below that. And the fact that we choose, you know, this is a particular parameterization that is one sort of human way to do it, just like we might invent some system of laws that would be one sort of human way to say how things should work. But it's sort of an interesting thing that there's kind of the law of unintended consequences is kind of the story of computational irreducibility and undecidability, so to speak. I mean, it's you know, that you don't get to, you know, when you kind of define, you know, tell the AIs what you want them to do, so to speak. That's kind of, you know, that there won't be any kind of system that we can invent that will say, you know, that's sort of a closed system that that will sort of guarantee the AIs do, quotes, the right things, so to speak.
Correct, and this may be the same reason. Wow, I mean, we went to so many deep things there. But yeah, exactly. So when Asimov came up with the 3 laws of robotics, they sound nice, but the thing is, you will have a very, very dumb closed robot, if that is even possible, to completely obey those axioms. But you're right, it will have surprises that you never saw coming.
Right. I mean, and you know, that's why, you know, in human legal systems, people always have to patch them. When, you know, who thought of social media when, you know, when the US Constitution was written?
Yeah, right.
Who thought of, you know, mind uploading when the US Constitution was written? You know, these are things where sort of the actual sort of irreducible, you know, things that happen in the evolution of the world, you know, necessarily sort of escape any kind of boxing in from some kind of set of axiomatic constraints. I mean, I think it's something where, you know, computational irreducibility, for example, is a very foundational idea. I mean, it's a very obvious idea, actually. It's kind of fun for me because, you know, I came up with this thing in the 80s, right? So there are plenty of people who, you know, I interact with now and who work with it, who were born after it was invented.
I see.
And so for them, it couldn't be any other way. It's like I mean, for me, it couldn't be any other way either. I'm so used to it. It's kind of, but at first, when you first hear it, it's kind of a bizarre thing. And it's like, no, we can get our science. Our science is going to triumph. You know, science is going to be able to solve this. Science, you know, in fact, this is in a sense, and we've seen this a lot in this pandemic. It's kind of like people are saying, science is going to solve it. Science is going to predict what's going to happen. Science, we're going to know what's going to happen. Well, you know, it's kind of funny if you look at the sort of long arc of intellectual history. I mean, you know, before Copernicus, people were like, look, I can tell the Earth isn't moving. It's sitting right here. I'm on it. It's all good, so to speak. And then, you know, along comes Copernicus and says, by the way, I can kind of scientifically prove that, you know, the Earth is moving, and the fact that your senses say that isn't the case is just your senses are not sophisticated enough. And so, you know, that led to, over the last 500 years, this sort of increasing belief that science has it. Science is the way to figure stuff out. And the concept that science will just eventually get everything. Science will be able to answer every question. And people have a very intrinsic belief in science now. It's kind of ironic that it is as, you know, I think it's as strong a faith, so to speak, as any kind of religious faith ever was, that science will have it. You know, science will solve it. Then comes computational irreducibility. And we see, well, actually, that's not really true anymore. And what's interesting about computational irreducibility, it's kind of science eating itself from the inside. It's an idea that comes out of science. It's not an idea that came out of some, you know, mystical whatever. It comes absolutely out of the mainstream tradition of science. And it is something where you can use the methods of science to establish this thing that basically says science has limitations.
Exactly. Yeah, beautiful. Exactly.
I mean, I think that, and you know, one of the things that I think is we are in the very, very, very early days of understanding what that means. I mean, you know, from Copernicus, so to speak, we have the idea that, you know, science tells us things that aren't obvious to us. Things like computational irreducibility are things we now learn from this kind of computational paradigm for thinking about the world. And I kind of view, you know, people ask me about the, you know, fundamental theory of physics. Who cares whether there's a fundamental theory of physics, right? And it's also like, who actually cares whether the Earth goes around the sun or the other way around? You know, it's ironic that like when we do astronomical calculations now using, you know, all of these sort of series approximation type things, those could be epicycles. It doesn't make any difference. It's like, you know, okay, Ptolemy had 5 epicycles. We have 100,000 epicycles. You know, we're computing, you know, that's how we do practical ephemeris computations, so to speak. So it doesn't, but it has the conceptual effect of knowing that something is happening that isn't obvious to us from our senses is really important. And so similarly, from, you know, from knowing that the universe is computational all the way down, basically is a great big banner that says, you've got to take this computation idea seriously because it's how our whole universe is made. I think that's kind of the, and so things like computational irreducibility, which from a, you know, thinking about the world and thinking about what can we constrain, like with the AIs, you know, we say, okay, we're going to constrain the AIs with Asimov's laws of robotics or something. No, that couldn't possibly work. And as soon as you understand computational irreducibility, you kind of immediately know, totally, you know, not going to work. And it's like, you know, I was doing some testimony for the US Senate a couple of years ago about, you know, constraints on kind of, you know, how you rank content from the internet and so on. And it's like, okay, let's say you can just, you know, tell people, just show us your code and say that, you know, we'll have an agency that vets the code. And it's like, that can't possibly work. You know, but it's obvious it can't possibly work. As soon as you understand computational irreducibility, it's obvious it can't work. Just as from sort of the mathematical tradition and understanding things like energy and momentum conservation and so on, there's certain kinds of things that you can immediately say in the world couldn't possibly work from that intuition. But I think that the, you know, this, well, one thing that's been interesting with the physics project is that, you know, computation was this sort of paradigm that one comes out with ideas like computational irreducibility. I view our physics project as kind of the initiation of what I'm sort of describing as kind of a 4th paradigm for science. And I'm very greedy to think that I've, you know, been involved in 2 paradigms out of 4. But it's, you know, I think that's just a consequence of, you know, one doesn't get to pick the time in history where one lives, but one can be lucky in those respects. But you know, I think the sort of the first paradigm was the one in antiquity of kind of, you know, what are things made of? Things are made of atoms, things are made of this. And that's kind of, you know, that's the paradigm of science that we're still in for many fields of science. It's just, what are things made of? Then, you know, then we get to the 1600s, we get mathematical science, and we get this idea of things are described by equations and so on. Then the 1980s, this kind of computational idea. And then now the computational idea, what one's saying is, here's a rule, run it, and that represents what the system does. In the physics project, there's a slightly different idea, which I call multicomputation, which is the idea that you have a rule, but it can be applied in many possible ways. That leads to kind of many threads of time. And to know what happened, you have to have an observer. It's not good enough to just say, here's the system, run it and see what goes on, because you have all these threads of time and there's no notion of what happened unless you're saying how you're parsing all those threads of time. I mean, from a sort of computer sciencey point of view, it's like the ordinary computation thing is like an ordinary deterministic Turing machine that has, you know, that just follows step by step.
One
thread of time. Whereas, you know, people sometimes talk about non-deterministic Turing machines where they can do different things at different steps. Almost always where people talk about that, they mean, they're saying, well, it could in principle do different things at different steps, but all we actually care about is this one path that gets us to the answer we want.
Right.
And so, for example, in the P versus NP problem in computational complexity theory, one's saying, well, you know, we've got numbers, we can multiply them together, that's pretty easy. But if we want to know of a given number, what are its factors? That is an NP problem in the sense that non-deterministically, if we could guess the factors, we can check it easily, but we have to try all those different possible factors potentially to get the answer. But what people imagine there is they're thinking, but there's going to be one right answer. That's all we care about.
Right.
What we're now talking about in multi-computation is the full multi-way graph, all possible things that can happen, because that's what we think the universe does. And we think that we, in a rather bizarre way, quantum mechanics is the story of all possible things happening. And our perception of quantum mechanics, and this is where things get very weird, is that we are embedded in a universe which is branching all the time. There's many threads of time, but our brains, our minds are also branching that way. So in a sense, quantum mechanics ends up being the story of how does a branching brain perceive a branching universe. And that's which is a, you know, because in other words, it's just like this thing we were talking about before about persistence in time. If you believe that definite things happen, then you as a branching brain have to conflate those different threads of time. You have to say, I'm going to assume they were all the same because I think something definite happened. Now, that could blow up on you. It could be the case that as you go forward in time, your assumption that those two things were the same becomes just completely inconsistent. And the statement that that doesn't happen is one of the conclusions of the physics project that is a little bit complicated to talk about, but that's to do with this causal invariance business and so on. But the thing that I mean, this notion of multi-computation, you follow all the branches, you actually look at all the branches. It's like, imagine you play a game, you're playing, you know, tic-tac-toe or something. You follow one path.
Right.
But there is a whole tree, a whole graph. Actually, it isn't just a tree, it's a graph because things can merge of things. And I think it has 4,000 nodes for tic-tac-toe. And just think about the whole thing. And so that idea of sort of the think about the whole thing idea and the notion of, but then there's an observer who picks out a particular part of it. That is, I think, sort of this different paradigm for thinking about time, this different paradigm for making models in science. And the thing that's just really amazing, it's the thing from the last few months, is the realization that there are just, you know, well, when I thought about simple programs and sort of how you make complexity with simple programs, there were lots of kind of science questions where it's like, we're blocked in this field of science because we don't know where complexity comes from. So then we kind of got that one, you know, sorted out. And now we're blocked in a bunch of areas of science where it seems like we can't say anything. You know, whether it's like biological evolution, explain why there are higher organisms like us, rather than, you know, the fittest organism was actually a virus. You know, we can't explain that. There's no, you know, Darwin thought that there would be essentially, I mean, the very last sentence in Origin of Species says, you know, while the earth goes around the sun according to the fixed law of gravity, so new species, ever more complex, I think that's the word he uses, will evolve, right? So he thought there will be an inexorable, essentially mathematical law, like the law of gravity, that leads to us rather than the viruses, so to speak. But nobody's ever found that. Nobody knows why that's true.
Your friend Gregory Chaitin has a proposal here in proving Darwin, where he has a very simple model where he uses, it's a very interesting mathematical model of evolution where he shows necessarily you need to get something more and more complex because you're really trying to solve the halting problem. So
right, so his idea, which is a very lovely idea, his idea is that if you are competing, there is, it's for the same reason as all of these computational irreducibility things and so on. You'll never find the ultimate winner. Now, I think that and yes, that is, I think, the most promising kind of direction in terms of explaining why there are higher organisms and so on. I'm not sure. I have to say, Greg and I did actually a live stream discussion a little while ago about this.
I saw. It was great.
You know, yeah. So I mean, I think that is a very reasonable kind of, I think, direction towards answering that question. But I think the issue is, in a sense, can one really say there is a sort of okay, here's another one which that doesn't really get, which is, why are there species?
Yeah, his model only had one species, one organism. So yeah, you're right. Yeah.
Right. So I mean, he's chasing, but it's not clear why you should break up into species. And then people say, well, there's reproductive isolation, et cetera, et cetera, et cetera. But there's, it's not clear why that happens. But, the main point is, what is the kind of framework? Would you expect biological evolution to be described by what kind of a model would encompass it? And I don't know yet. I mean, this is still speculation that there will be some kind of multi-computational model. I have some definite ideas about how that might work, but don't know if it will work. I think, well, the other one that is, there are many of these. I mean, this sort of idea of multi-computation. So let's go back to P equals NP, for example.
Sure. Yeah.
Computation theory kind of thing. So that's been a big question. Is it possible to, you've got these deterministic Turing machines, and you've got these things that can be answered by a non-deterministic machine where there is a path to answer it, but you just don't know which path it is.
Right.
And so that turns out to be essentially a geometrical question in terms of these multi-way graphs. So in a sense, what you have, okay, so you have a Ruliad multi-way system in which you're looking at all possible Turing machines evolving in all possible ways, and they generate lots of states. You can then, a sub-part of that thing is the deterministic Turing machines. So in a sense, it becomes, is this region that is described by the deterministic Turing machines, does it eventually reach as far as the region described by the non-deterministic Turing machines? Right. Now, again, not figured out yet, but I think we have kind of a beginning of a sort of geometrization of that kind of question. So that's, I mean, that's sort of a coming attraction. I mean, I will say in terms, oh yeah, there we go, beautiful. That is exactly. I am very pleased with how much you know of my efforts.
I've been really trying to do my homework. There's a reason why when I contacted Danielle, thanks Danielle, it's because I was brushing up, doing my homework before speaking to you. So. Good.
Well, yeah, no, it's great. No, that is absolutely, that's a fine Ruliad multi-way system, and the red pieces are the pieces that can be reached by a deterministic Turing machine. And the question is, in the limit, does the red cover everything? And that's the P equals NP question. I mean, I might say, by the way, that there's sort of I mean, I'm slowly getting towards kind of a theory of distributed computing. This is another piece of this whole thing. I mean, there's so many, it's exciting because, I've been involved in inventing, some number of ideas in my life, but I have to say that the current time, the rate of kind of things where, oh my gosh, this thing I've been thinking about for 40 years, there's actually a path to potentially be able to answer it, is outrageously high. And it's very, it's very bizarre experience, I would say. But, one of the things that I've been interested in for a super long time is we think about computations, and we essentially think about as sort of a representation of the ongoing process of computation. And well, this is a bit hard. Again, it's always so hard to explain things when one doesn't yet quite understand them. But anyway, the end result, I think, will be that we will have kind of a principled theory of distributed computing, in which most approaches to distributed computing, it's like things can happen in parallel, but in order for us humans to write programs, we have to synchronize stuff so that at some point we wait until all the parallel things have finished, and now we can go on and do the next thing. The universe doesn't wait like that. The universe is just doing things in parallel all the time. And I think that some of the science that we've got from thinking about the universe can be used to understand how we can do computation in a sort of distributed all the way through kind of fashion. I think one application of this is probably to molecular computing, where I have a bunch of ideas about how you can kind of do computations where sort of the answer is in the configuration of molecules in a way that is a little different from the way people think about doing computation now. And so that's, I mean, it's a very fertile collection of ideas. And another one that sort of been playing with, but I don't really have good, hasn't landed yet, is an application to economics, where kind of the idea is at the lowest level there are just transactions happening, and that's like at the lowest level they're just atoms of space doing their thing.
I see.
And the question is what emerges at a higher level. So, for example, the notion that it could be the case that there's only kind of local transactions, that all we know about is, oh, I bought that thing from this person, and it, sort of barter all the way down. But in fact, we know that in economic systems there is an emergent global property, like things like a price, for example.
Right.
Your friend Nassim Taleb told me that the correct term is a numeraire.
Right, I remember that part of the talk. That's right.
That represents it was very useful to know that buzz term, because that allows me to go chase the literature, so to speak. I think that then the notion is what that there is this globality, that even though everything is really locally, you're just buying something from this person who's buying something from that person, that something global emerges. Feels like the same kind of thing as the emergence of space from this, from the details of what happens with atoms of space. Same kind of thing as the emergence of fluid mechanics from the details of what happens with individual molecules. And sort of my personal test for whether I know what I'm talking about is, can I make a practical distributed blockchain using these ideas that that in which there is something like a genuine notion of price and value and so on. And actually the way this happened in 2020, the physics project had come out, and I was thinking about, there were potential applications. And so, one of the potential applications was what I was referring to as quantum money, where because in a blockchain, what you're doing is, in the blockchain, you have the single ledger that represents the transactions that have happened. And it's a very sequentialized thing.
Correct.
And it's very inefficient to do that, because you kind of have to have everybody coming to consensus about what's going on before
synchronization. Humans need to synchronize, like you say. It doesn't need to be
right. But so the idea was, what if you don't do that, but you have this notion of things haven't quite synchronized, and if you want to know what your bank balance is, and you want to know really quickly what's my bank balance, well, there will be some uncertainty. Like the uncertainty.
Eventual consistency. The problem appears there. Yes.
Right. I mean, it's only, and then what you have to do is, over time, statistically, there is a high probability that the uncertainty will go down. And you could have picked, as we were working on this, it was like, somebody eventually drives the car off the lot, was the analogy we were using. And that's kind of like measurement in quantum mechanics. Eventually the cat is alive or dead in the, Schrodinger cat story and so on. So, what that kind of backed me into was realizing, gosh, I actually don't understand how economics works at all.
I don't think anybody does.
Well, yes, but perhaps not. But and then I was, I was trying to understand, what can we say? For example, it could be the case, if we're looking at physics, there are certain global laws of physics. There is a notion of space. There's a notion of time. There's a notion of gravity. If we're looking at a gas, for example, there are the gas laws, the pressure, temperature, volume relations, and so on. But there's also a lot of detailed stuff that's happening at the level of individual molecules that we don't talk about very much. We've chosen to talk about things where we can make fairly simple laws. Now, in economics, what are the things about which we can make simple laws? It's not obvious they're the things we've looked at so far. And particularly in modern times, when there's a lot of microscopic data that exists, it could be the case that there is a great economic theory. It just happens to be about some bizarre, it's not about velocity of money, it's about some weird vorticity of money or something that is some quantity we've never looked at. And there is a global law of that, even though there isn't a global law of some of the things that we've more obviously looked at. And so that's an example of how, how one could end up with, how there could end up being a theory of economics. It just isn't the kind of theory we thought it was. you know, I think the issue is that there is a theory of physics is not self-evidently the case. I mean, there's a thing the theologians talked about, you know, the fact it's the kind of argument by design for the existence of God is this kind of thing about saying, why would the universe have laws in it if it wasn't made this way for a purpose, so to speak? Why does the universe operate according to laws? And a corollary to that would be according to laws that we humans can even vaguely comprehend.
Which is a mystery until recently, I think, and your advances, I think, helps to explain it.
Yes, well, I mean, I think that, but in a very bizarre way, because in a sense, what it says, I mean, I think Einstein was famous for saying, you know, the most incomprehensible thing about the universe is that it's comprehensible to us.
Right.
I mean, it's a kind of thing where what one's you know, in a sense, what our physics project is kind of showing is that in some sense it's a self-fulfilling prophecy, although not quite. In other words, given our forms of perception, there are certain kinds of things that we are sensitive to in the universe.
Mm-hmm.
Now, it is then a mathematical fact that it is possible to put together laws in the ways that we put together laws. It might be the case that given an alien species, so to speak, that evolved with certain sensory apparatus and that existed at a certain size, you know, let's say the alien species was the size of a planet and, you know, used, you know, did this or that thing, it might be the case that given, you know, if we're just presented with, here's your sensory apparatus, here's how big you are, we might not be able to construct laws of physics along the lines that, you know, that fit together in the kinds of ways that our laws of physics fit together. Presumably, the fact that we have the sensory apparatus we have is a kind of co-evolved fact with the fact that that allows us to put together laws of physics. But so, I mean, in a sense, what we're doing is we're saying that the universe is comprehensible to us because it is a mathematical fact that with sensory apparatus like ours, there are certain laws of physics that necessarily are what occur. Now, in economics, for example, I suspect there's an analogous thing. I suspect that the notion of price, for example, which is a notion that makes economics much more human accessible, so to speak. Without a notion of price, if all there was, so imagine a future of economics in which it's bots all the way down, that no human ever, you know, I don't, you know, try and buy a piece of chocolate. Instead, I just tell my bot, I kind of want a piece of chocolate. Okay, go out into the world, make a series of barter transactions, which eventually will wind up with, you know, the cocoa plant being harvested in this place, and eventually the bots will deliver me a piece of chocolate. That process and knowing, can I afford a piece of chocolate, will be incomprehensible to me. I mean, it's like the bots go off and a chain of 1,000 bots leading to...
Let's say they had to do things like hashing and so on just to be able to do, I don't know, add it to a ledger. Right. But
more than that, it's like, I'm going to trade you, you know, like, what do I make? I make software, right? In the end, let's trade the software for the cocoa bean that came off this tree. And, you know, that's a complicated series of transactions that you have to, you know, and no doubt, you know, one cocoa bean isn't worth the same as one piece of software, and it all has to get broken up. And, you know, you've got to have all these things where you're comparing this to that, and you're figuring out, oh, this has to be transported to here, and so on and so on and so on. You're doing all that work. And as a human, if I ask the question, can I afford a piece of chocolate? The answer will be, I don't have a clue. You know, I can send off my bot might come back and say, yep, you can afford, you know, 1 million pieces of chocolate. Or, you know, you can afford 3 pieces of chocolate, and I don't have a clue. But so in a sense, the notion of price is a humanization of that process. It's a way of turning what would otherwise be this incomprehensible, you know, complicated, irreducible computational process into something where I'm going to say, I'm just going to describe this by saying the chocolate costs $1 a piece or something. And that's a kind of a global statement. So the fact that we have set up our, you know, that it is, you know, so it might not be consistent. So that's an interesting point, that you might say the chocolate costs $1, but the way the world actually works, it might not be consistent to name a fixed price for the chocolate. So And that's, and no doubt you can think of that as being, the various, I don't know, event horizons that exist between, non-interconvertible currencies and things like this. So like an event horizon where you can't kind of communicate. There's no causal connection between transactions happening on one side and on the other. Those kinds of things. Except, but I mean that's but so I think this is the kind of thinking, and the question then is, if you say, we have sort of smoothed out all of the kind of complexity of underlying economic activity. We've smoothed it out into these human describable things like price. Can we then deduce global laws for that in the same kind of a way that we deduce global laws in the case of physics? But those global laws, in the case of physics, the global laws are a good match for our sensory data. We can see that supernova explode with our eyes, type thing. It's not something where we have to, where it's it's some sensory apparatus that we just, don't have. And in economics, that's the question of whether the things about which there are simple laws are things that our sensory apparatus, so to speak, allows us to know about. And I do think, and I haven't really thought this through properly, but I think that the fact that there's so much microeconomic, microeconomic data, so to speak, that exists today, I don't know what people are doing with it. I mean, I think that in some sense, it's like in chemistry, I'm claiming that it isn't enough to just say, what's the total concentration of molecules? You might need to know the causal relationships between molecular interactions. So similarly, the same thing might be true in economics, that it might be that the interesting stuff that happens with respect to some quantity or some measurement that isn't the one we immediately pick. Anyway, these are so let's see, what fraction of your potential topics did we cover? I think we didn't cover
quite a lot. So we went through. It's interesting. I like that we didn't take a linear walk of the project. We ended up with Ruliad space anyway, which is great. And I'm sorry, I want to be very mindful of your time also. So if you want to continue,
I do have to disappear soon. Unfortunately, I've got to dive back into mathematics. Actually,
gotcha.
In the effort to finish my tome about mathematics.
Absolutely, and I think that's more important than perhaps if you would be so kind, and if not, it's okay. We can continue the other half of the topic I wanted to go to next time, perhaps.
Yeah, this is fun, but maybe we take one more topic. I think you had a bunch of things around the notion of IQ.
Sure. Yeah, let's quickly go through that. Yes.
Which is a topic that I haven't thought that much about. Let's see, maybe you have.
So I actually used your, what happened here? Oh, because we opened new tabs. So I actually used your idea. So this came from Nassim's Twitter fight actually about IQ. A bunch of people were making very unscientific statements about IQ.
Okay, so I mean, I can tell you my view of this. I mean, I think I don't know about this particular Twitter fight. Nassim gets into many Twitter fights. I'm afraid I'm aware of essentially none of them. It's his art. They're very amusing in many cases. Sometimes I don't agree with him, but I think boy, okay, this is a long tails argument. That's interesting.
He has a very interesting statistical argument about why it doesn't actually work by adding noise and so on. I haven't fully delved into it myself. I have a different argument actually, a computational argument for it's an independent argument from his.
But look, I think that the question is, it's kind of a computational reducibility versus irreducibility question. Mm-hmm. You want to know, if I have this person, are they going to be able to solve this type of problem, do this type of job, whatever else, right? And it's saying, is there a single quantity that I can measure that will determine this infinitude of possible outcomes? It's just like, can I just measure one number and it'll say, this person can do this and that person can do that? It's pretty obvious that's not going to work, for the same reason that you can't, get sort of through this narrow, you can't just sort of say, and this is how the AIs should work its 3 laws of robotics. You can't say, given that the parameter for this person, I measured this quantity for this person, and therefore I know they will be able to solve this research problem in physics type thing. It just doesn't, that's not a plausible thing.
Exactly, because it implies that you can shortcut them, which, from your findings, that's obviously not true, generally not true.
Yeah, right. So I mean, in some sense, that kind of immediately tells you that nothing like a number that represent, I mean, depending on what you want IQ to represent. If you want IQ to, I think in modern times, isn't, IQ is the new divine right or something. I don't know what the thing is. It's kind of the it's often viewed as, look, all the smart people are going to the fancy schools and are going to run the world type thing. It's kind of become this kind of but it's a very bizarre idea, because it's kind of this notion that this sort of whatever happens in the world, this one parameter is going to determine whether people do the right thing, et cetera, et cetera, et cetera. And it's just sort of obviously not true. And it, is it completely useless? Well, it depends what you're using it for. When it was originally invented in the 1930s and so on, it was a, I mean, as a person who has over my life sort of found and employed many talented people, it's with a wide diversity of types of people and talents, so to speak. It's this whole question about how do you identify certain kinds of a talent for this which can be fitted into this. Super interesting question. This is an extremely blunt instrument for doing that.
No, absolutely.
And I think I think it's it's kind of a shame, in a sense, that some people, it's one of these things where the extent to which people believe one of these sort of ideas that, if you get a good SAT score, then and you go to a good college, then that means that you're, able to figure out things in the world type thing. I mean, I would have to say that I think maybe this is one of these things I shouldn't say, but I have to say that watching the pandemic unfold and watching some of the kind of sort of things people have said and not said about the science of the thing, I have to say I'm pretty unimpressed with the, if that was, if the people who were sort of filtered down to be the people who were kind of doing all that stuff were filtered by a thing that is like an IQ filter, then it did a really bad job, because because in fact, it's sort of interesting that people, sort of the lack of understanding of the kind of broader picture of what science can figure out, what science cannot figure out. It's like, yes, I took a science class and we were able to solve the exercises in the book. Therefore, we can solve everything we need to solve.
Yes.
About how the world works. Turns out not to be true. And but to know that it isn't true, you have to kind of go outside the bounds of the IQ test, so to speak. If you live in an IQ test, then that will seem to be true, because you can win the IQ test, so to speak, with a complete belief that that's true, because it doesn't, that there's nothing about kind of, and there's other things that happen in the world and so on.
There's no surprises, right? Yeah, exactly.
Right. It's anyway, look, a lot of interesting topics, and cool. Okay, so you've kind of you've set me up, I suppose, for a part 2, because there are lots of interesting other topics to discuss. But
only if you'd love to come on again. It was a pleasure chatting with you. Thank you so much for your time. I really appreciate it.
It was great. Thanks. All right, I shall disappear, and hopefully this recording will make its way to you.
Yep, I'll ask Danielle. Great. Thank you. Thank you so much.
Okay. Bye-bye.